Hello and welcome to the Screencast introducing infinity, limits, and power functions. In earlier work this semester, we studied several different functions that increase without bound as the input variable increases: x squared, e to the x, and the natural log of x. In this section, we use power functions, functions of the form x to the nth power, as a way to study additional patterns around unbounded behavior. And we also considered the elementary rational functions 1 over x squared, and in general 1 over x to the nth power. Mathematical notation provides a way to succinctly express patterns in relationships. When discussing functions whose value increases or decreases without bound, we use limit notation to show this. Previously, we have written statements like, as x increases without bound, e to the x increases without bound. Now, we'll write this even more precisely as the limit of e to the x as x increases without bound equals infinity, which means that we can make e to the x as large as we would like by letting x be sufficiently large. One of the important skills to develop in preparation for calculus is familiarity with the long-range behaviors of a library of basic functions. It will be helpful to you in many ways to be able to envision the graphs of x squared, x to the third, 1 over x squared, e to the x, the natural log of x, and many more. An important skill to develop in preparation for calculus is also familiarity with the behavior of functions near a finite value a. For example, given f of x equals 1 over x squared, we see that the outputs increase without bound as x approaches 0. We can use limit notation to show this behavior as well. The notation, the limit of 1 over x squared as x approaches 0 equals infinity, means we can make the value of 1 over x squared as large as we'd like by letting x be sufficiently close, but not equal, to 0.